Is there a single value that is out of the range? Let me see. So U0, yeah, okay. So this is not good. What happens to that? Debugging time. FU interface is initialized at zeros. Yeah, I wanted to use a zero boundary condition, which makes the boundary values to be zero. Okay. So that is the right. So what happened is let's look at what my U is. My U is negative and negative. So my U, okay. So let's say between the first volume and the second volume, both value are negative, and UL is less than UR. UL is less than. Okay, so my U left is less than U right. So I'm getting to this. Okay, FU interface would be the minimum of FU bar I left and FU bar I. Okay, and in this case, because FU bar is U square over 2, what I get is the minimum of these two, which is going to be, oh, I see the problem I have. Because the left side is always negative, so it is going to have a solution that keeps going towards the left. And at the zeroth interface, I set my flux to 0. So that has a problem, because I should be taking the flux from the right, while I'm taking the flux at 0. So what I should be doing is this. What I should be doing is, if I have a zero boundary condition on two sides, what I should be doing is make a U that is equal to 0, U0. So basically, I put two ghost cells on the two ends of the solution. Okay, and then when I'm computing the interface flux, I want to do this from 1 to n plus 1. I want to go through the whole region, including the interfaces at the two ends. And then I think instead of ui minus 1, I have ui and ui plus 1. And this is taking ui and ui plus 1, right? Because now the index of u and the FU interface is shifted. So wherever I go, I need to change ui plus 1, ui minus 1 to ui, and ui to ui plus 1. And this is ui and ui plus 1. And du dt equal to this divided by this. Okay, now I'm properly taking du df bar. Okay, I'm no longer using du df bar, so I get rid of this. You see what I did to fix the boundary conditions? So what I did is previously I assumed that the numerical flux at both ends are equal to 0, which means I'm always taking the value of the flux at the boundary, even if the characteristics are going from the interior into the boundary. Okay, so that is wrong. That is wrong because I cannot always enforce the boundary condition. And I cannot enforce the boundary condition if the characteristics are moving from the interiors towards the exterior, right? So if I get a, let's see, go to my lecture. So if I no, not this one. If I have a T and X diagram, and if this is my boundary, if my characteristics are moving from the interior towards the boundary, then there is no way I can say, okay, the value of the boundary has to be a certain value, because the value at the boundary at this time has to be the same as the solution over here, right? So the value comes from the interior, not from outside the boundary. I can only enforce a boundary condition here if the characteristics are going in. So that is the tricky part that I missed in the original code. Left and on the right of this outside the boundaries. And on the go cell, I set the value to be 0. That is the line of code. That is the line of code here, right? I put a 0, which is a go cell in beginning and end of this array. And I computed the flux over here according to the Godonov flux using the ghost cell and the first cell in the boundary. And that takes care of things, because if the characteristics are moving towards the outside, then I'm using the flux value from the inside. If the characteristics are going inward, then I'm using the flux value from the boundary condition. Okay, is that clear? So yeah, so I figure it would be useful to illustrate this, because if I make a mistake, that means it's a mistake that can be easily made. I think it'll be useful for you to learn my mistake. All right, so is it clear what I did wrong and now how I fixed it? So let's see that again. Do I need to what? No, I don't need to change the DUDT, because here U is passing as a length 128, right? Here I appended U to be length 130. Okay, but FU interface is still of the size 129. And here when I computed a DUDT equal to FU interface 1 to the n minus 1, this is length 128, this is also length 128. So I'm only computing DUDT for the interiors. Yeah. And this is your function. 128, 0. Oh, I need to close that one first. Okay. And let me draw roughly the same function, minus 0.8, jumps to 0.8. Okay, and I get a U0, and I'm going to do the for loop again. Oops, I don't want this. All right, and let me close this first. Yes, now I get a proper solution. The values at both ends are going towards the outside, so it doesn't accumulate the flux over there. Okay, very good. So now we have a proper implementation of the Godonov scheme. Any questions before we move to second order? Yeah. Yeah, there seems to be a kink in the middle. That's a good question. So it is there is a non-smoothness in the middle, and that's a very good observation. And the size of the jump between these two seems to be about twice the jump nearby. So basically, over here you get 0 flux, right? And over here, you get flux from the right hand side. Right. So there is always so the Godonov scheme, as we said, is first order accurate, and this I think is a manifestation of that. So if you refine the grid, you're going to see this is going to be less. Actually, it is more obvious. For example, if we coarsen the grid to be 16, and I think we'll see that a little bit clearer. And my guess is that you are going to see that as more obviously. So it's going to be, did I do 16? Yes, you see the gap in the middle is like more obvious than before. So basically, as we refine the grid, that's a good motivation for what we are going to be discussing next. All right, let's take maybe 3 minutes break. By the way, the Godonov scheme is not obvious at all. I had no idea how Godonov came up with this at the beginning. It's like you have to really think through every possible case to convince that like it actually works as intended. So it's very interesting to see that like you can reduce all the cases to only these two very simple cases. Exactly, there is no need to track the discontinuity. And it becomes impractical to track any discontinuity when you go to a system of equations, because they can like appear from anywhere really. If that's right, and you can also have a shockwaving like a combination of several variables, but not in other combinations. So it's right. If you have A and B, you can have a shockwave in A plus B, but not in A minus B, or some even weirder combinations. This will take care of everything, right? Exactly. It prevents shocks. It prevents like exact shocks from forming if you solve the equations exactly. But in reality, I don't think. In reality, for example, if you solve in fluid flow equations, the viscosity is usually so small that like the this flux term that does not have derivatives is really going to overcome the viscosity near the shock waves. So you still get like for the grid you are going to be using, most likely you won't observe any difference in the regions of discontinuity. I mean, you won't say it is not a real discontinuity. Still looks like a discontinuity numerically. Yeah, if you refine the grid like crazy, you may be able to see, okay, it is not really a discontinuity, but like